Well, welcome back. I thought that we would benefit from seeing a couple of examples of Taylor series worked out, generated, so that you could get comfortable with the process and see how these things work really. So example one was in a content video. So let's find the Taylor series generated by f of x equals sine x at x equals 0. So we're going to find a Taylor series generated by this function at this is the a value. Suppose that should be the a value, right? I suppose that should be. So let's do this. We can do this. We just need derivatives, and those are pretty easy to come by. We know what the first few derivatives are, and so we kind of write them out. I usually go at least 3 derivatives. Sometimes 4 are helpful. Sometimes I just get stuck on Roman numerals. This is by modern textbooks written that way. We figure out what all of those are at 0. So we figure out that at 0, that's 0, that's 1, that's 0, that's -1, that's 0, and then this process repeats. 0, 1, 0, -1, 0, 1, 0, -1, and that goes forever. So when we write the Taylor series, it's 0 plus first derivative times x minus 0 plus second derivative over 2 factorial times x minus a squared plus third derivative over 3 factorial times x minus a cubed plus, and it goes. There's an x, there's a -1 over 3 factorial x cubed, there's a +1 over 5 factorial x to the 5th, there's a -1 over 7 factorial x to the 7th, and so on. So we know that it alternates. We know that there's a factorial. We know that there's an x to the power, and they match. So how do we say only use the odd ones? Well, usually we look at 1 as 2 times 0 plus 1, and 3 as 2 times 1 plus 1. That's how you get your odds. So we can just call this 2n plus 1, and this 2n plus 1. If n is 1, we get a negative. If n is 0, we get a positive. So we kind of want it to look like that. And it goes on forever and ever. This will be a Taylor series that will converge to sine x. So what does that mean? Oh, this is exciting. What does that mean? That means, oh, mercy, here. You didn't want any of that. This is happening live. That's sine x. So if we also graphed x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, we would notice that that is really close to sine x in an interval centered at 0, because a is 0, that's the center. And the more terms we add, x to the 9th over 9 factorial, x to the 11th over 11, the more terms we add, the closer this stays for longer. And you would find that if you added more and more terms, that's exactly what goes on. That's what we talk about when we talk about converging. And in fact, if we were to run the ratio test to find the interval of convergence, we would find out that this Taylor series converges to sine x for all x. One more. Find the Taylor series generated by f of x equals e to the x at a equals 1. And this also turns out to be unburdeningly okay. All the derivatives are e to the x, and all of them evaluated at 1 are e, all of them. So when we go to figure out what the Taylor series is, how does this work? We say f of 1, f prime of 1 times x minus 1, f double prime of 1 over 2 factorial times x minus 1 squared, f triple prime of 1 over 3 factorial times x minus 1 cubed, and so on. A derivative, a factorial, a power, all the way through. Generically speaking, it's going to look like this, and it goes. If you were to graph the first few terms and you were to graph e to the x, you would find out that they match very closely in an interval centered at 1. They're precisely the same at 1, and as you move away from 1, it stays close for a while and then gets further away as you move further away from 1. Okay, I hope this is helpful for repetition's sake, and we'll talk more when we gather in class. Thanks, everybody.